Okay, so this is your quick reference guide for Module 4. Remember, these are all on the second page of your workbook. The inside of the front cover has little quick references to everything you need to know in each of the modules. And it kind of comes in two flavors. And the first flavor is the one that we're going to spend our time on today. It's the two things that are most important to know about slope. First of all, how does the slope of an equation fit together with the y-intercept to form an equation for that line, y equals mx plus b. This is your multi-tool. Pretty much any question that you need to answer about linear equations can in some fashion be answered by y equals mx plus b. But then the second part of that is the equation that defines the slope. What exactly is slope, and how do we understand what it looks like on a graph? That's the second formula, m equals y2 minus y1 over x2 minus x1, sometimes known as the rise over run formula, y2 minus y1 being the rise, x2 minus x1 being sometimes called the run. So whichever formulation you remember that in. Really, that's kind of what that equation is telling you. So that's the circle of ideas that we're most interested in our work today. So let's take a look back, and I kind of just want to talk about the first problem that we looked at. This is problem number 3. And then also I want to look at together at problem number 5. So the problem number 3 comes from goal topic 5a, in which the question is, how do we use the slope and the y-intercept of a line to understand how to graph that line? And then question number 5 comes from goal topic 5b, which is, how do we determine an equation for a line if we know the coordinates of 2 of its points? That, I think, is probably the keystone crown jewel skill for this module. And when I say 5A, 5B, I really meant 4A, 4B. I apologize. So let's start with question number 3. In this question, you're given an equation for a line, and it's given to us in a format that doesn't look like y equals mx plus b. And yet we're still called upon to discover the slope, discover the y-intercept, and then use that information to supply a graph for this line. So what was your strategy? What did you start out doing in this problem in order to determine what the slope and the y-intercept of this line are? Yeah, Robert.
Separate the, or get the y by itself.
Yeah. If you're given an equation for a line which is not in slope-intercept format, a good bet is to turn it into slope-intercept format. Turn into, ultimately, the slope-intercept format, y equals mx plus b, is characterized by having y by itself on one side of the equation. So our hunch is that if we can solve this equation for y, then we will know what the slope and the y-intercept are. So let's solve this equation for y. What are the steps involved with that process? Starting from negative 3x minus 5y equals negative 15. If I want to get the y by itself, what should I do first? Add 3x to both sides, exactly. This is why we spent time in Module 2 solving for equations in terms of other variables. This is where that skill plugs in. So adding 3x, because that doesn't have our y in it, it takes the role of an additive or subtractive thing that in the reverse order of operations we should do first. So we'll end up with something like 3x minus 15. Okay, and now that y and x are on opposite sides of this equation, what do I need to do to take care of the last step to get the y by itself? Divide by negative 5. Exactly. So here I'll divide by negative 5. And then this is a point where it's easy to screw up a step. When you divide an expression, you divide the entirety of that expression. And that goes for both the left-hand side and the right-hand side of this equation. If I divide the left side by negative 5, everything on the right-hand side gets divided by negative 5. And so, for example, that term that doesn't have an x in it up here, when I divide it by negative 5, negative 15 divided by negative 5 gives me how much?
3.
3. And so that becomes my constant term in my finished equation. But then the other term, the 3x, also gets divided by negative 5. So how would you like to rewrite 3x divided by negative 5? What's a way to write that that's a little easier on the eyes? I'm talking about this quotient. Right, so I can leave it as a fraction. If I do that, it'll look something like 3x over negative 5, which I'm not thrilled about. It's not that it's incorrect, but what I'd like is I'd like to be able to understand how many times x is that. In other words, if we were to fit it into this template, y equals something times x, what's going to go into this something box? 3/5 with the negative sign. Yeah. So I'm going to instead see this as y equals negative 3/5 x plus 3. It's not that it's different, it's just that it's written differently in a way that I think jumps out at us a little bit more readily to see what the slope is. So now we've succeeded in writing this equation in its slope-intercept format. What did we gain here? What did we win? What do we know now that we didn't know before? We know the y-intercept, and what is it? 3. How do I know in this equation that the 3 is the y-intercept? Yeah, it's the only constant term on the right-hand side. It has no variable. It's the constant term. Great. So that answers one of our two questions. What is the y-intercept? The y-intercept is 3. If we want to be really specific about this, we should probably give the y-intercept coordinates. So the y-coordinate of that point is 3. What would the x-coordinate of the y-intercept be? As an ordered pair, we would put a 0 in the x-component because the y-intercept is a point on the y-axis, and points on the y-axis have an x-coordinate equal to 0. So what that means is that we can place one point right there at 0, 3, and know that that point belongs on the graph of our line, 0, 3. Because the y-intercept, according to our equation over here, the y-intercept of this line is 3. Great, so that's one important thing that we won. What else did we win in converting this line into slope-intercept format? We won the slope. And the slope is? Negative 3/5. All right, so now it bears thought how to interpret that number. What does the slope of a line tell us about that line? It tells us which way it's going. Yeah, I couldn't have said it better. It gives us an indication of direction. Which way does this line go? How does it do that? How does the number negative 3/5 tell us about which direction this line is going? It's going negative. Okay, so we're getting a little closer. What does going negative look like for a line? Yeah.
South.
South. Well, okay. But every line, almost every line, goes south in some way or another. This line is going to go south as it goes which direction?
East.
There we go. It goes south as it goes east. Or as we go from left to right, we should see this line descending in its y values. So in other words, we're more likely to find a line that looks like this. So here's a line which would have a negative slope. Than we would to have a line like this. This line would have a positive slope because as we go from left to right, our y values are increasing as our x values are increasing. So we know for sure that we're going to have a line which is descending as we go from left to right. What do the 3 and the 5 have to do with it? What do they tell us? Where the next point is. That's usually how we use this information, yeah. I'm going to rewrite this fraction by giving one of its parts the negative sign. I'm going to give it to the numerator. So if I write it as negative 3 divided by positive 5, how does that tell me how to find the next point on this graph? What should I do? It's rise over run. So we have a rise of negative 3, and we have a run of positive 5. What does a rise of negative 3 mean? Yeah, it's a negative rise, so it's going down. It's going down 3 units. And a run of positive 5 means what? Horizontal. And if we're running positive, then are we going left or right? Right. So that's how this slope tells us how to find the next point. It tells us that from any point on our line, if I go down 3 and right 5, I will find another point on this line. And as soon as I have 2 points, according to the principles of Euclidean geometry, that's all I need. because then I can just connect those dots and we'll be home free. So if I go down 3, so from 0, 3, if I go down 3, that puts me at 0, 0. And then to the right by 5, that puts me over at 5, 0. Then, according to this, I have found another point on our line. I'm going to label it 5, 0. And as soon as I found a second point on our line, we have the green light to finish graphing that line, just by connecting the dots of the 2 points that we just found. And I'm going to try and do this reasonably accurately here. There we go. So notice what the general arc of the strategy was here. Let me finish our slope, -3/5. The general arc of our strategy was we were given a line, an equation for a line that we didn't recognize as being in slope-intercept format. So we converted it into slope-intercept format, letting us identify the slope and the intercept. We can plot the intercept and then use the slope to stair-step our way to a second point, allowing us to connect the dots and then have a completed picture of this graph. Helena's question is, how come we couldn't have seen it as a rise of +3 and a run of -5? So in other words, just take that negative that I decided to award to the numerator and give it to the denominator instead. So instead of down 3, what's that going to tell me to do? Up 3. And instead of to the right by 5, I'm going left by 5. Let's see what would have happened if we followed that strategy instead. From 0, 3, if I go up 3, I'll end up here at 0, 6. And then to the left by 5, I'm going to end up here at -5, 6. Well, guess what? That point's also on our line. So the most important thing about this problem is the line and not the individual points that we decide to put on that line. So if you decided to go up 3 and left 5 and you connected those dots, you and I would have drawn exactly the same line at the end of this problem. Another piece of good news, it doesn't matter if you reverse the role of the signs, as long as you're consistent. The important thing about this fraction that defines our slope is that the signs are opposite to one another. Because if I go up and left, or if I go down and right, I end up walking along the same line. Where I would make a mistake is if I tried to do minus on top and minus on bottom. Then I'm going to be going up and to the right instead, which would turn my line to go to a direction that it's not going. But otherwise, don't sweat the choice of where to put the minus sign in a fraction that has a negative slope.